Hello everyone, welcome to Principles of Communication System lecture series. In this video, we are going to discuss about quantization process, types of quantization and quantization noise. Quantization process. The quantization is a process that converts sample signals into an approximate quantized signal which consists of only a finite number of pre-decided voltage levels. In general, the quantization process is converts the sample signals into a discrete signal. So for example, this is the quantizer. The quantizer input is continuous sampled signal, and sampled signal is M. We apply to quantizer. The quantizer is converts the continuous sample signals into a discrete sample signal V. So this is the main function of the quantization. Quantization is a process of round-off or approximation. In quantization, each sampled value at the input of the quantizer is approximated or round off to the nearest standard pre-decided voltage levels. These standard levels are known as a quantization level. So for example, the voltage level is 1.74 is the quantizer voltage level, and the round-off value for 1.74 is 2. Let's consider one more example. The quantization voltage level is 1.34. Let's assume it's equal to 1.34, and round-off value it's equal to 1 volt. The quantization process take place the following step. The input signal is x of t is assumed to have a peak to peak swing of VL to VH volts. So this is the input signal. The continuous signal is the input signal. The input signal is x of t. So input signal we represent in terms of x of t. The peak to peak voltage swing is VL to VH. So VL is the lower voltage level, V subscript L is the lower voltage level, and VH is the highest voltage level. This entire voltage range been divided into a Q. So this is the entire voltage range we divide into Q. The interval of each size is delta. So this is the delta. So delta is the step size. Delta is the step size. So delta it's equal to what's the highest voltage level VH V subscript H minus what's the lowest voltage level. The lowest voltage level is VL divided by L, where L it's equal to L it's equal to 2 to the power R. R is the number of bits. R it's equal to number of bit value, and quantized signal is xq of t. So x of t is the input signal and quantized signal is xq of t. So in this particular example, quantization level varies from q0 to q7, and step size it varies from delta 0 to delta 7. In this figure, the values of q it's equal to 8. So this is the first one and this is the last one, and number of levels are 8. It varies from q0 to q7, or the quantization level are also called as a decision threshold. Let us assume, for example, this is the first level and voltage is 0 0 0, and this is the last level, voltage is 1 1 1. xq of t, so this is the xq of t is the quantized output or round of value that represent the quantized version of x of t. We obtain xq of t at the output of the quantizer when x of t in the range of delta naught. Then the corresponding to any value of x of t, the quantizer output will be equal to q naught. Similarly, for all the values of x of t in the range of delta 1, the quantizer output will be equal to q1. For example, so this is the 0 voltage level, this is the 0 voltage level, this is the voltage level 1 and this is the voltage level 2. So here we have to find out the q1 value. This is the q1 and this is the intersect point. Here our main intention is to find out the voltage level. So voltage level between 1 volt to 2 volt. So this is the voltage level. Let us assume voltage it's equal to 1.6 volt. So q1 voltage level it's equal to 1.6 volt. The approximated value for 1.6 it's equal to 2 volt. In each range from delta 1 to delta 7 or delta 0 to delta 7, the signal x of t is a roundup of to a nearest quantization level and the quantized signal is produced. The quantized signal xq of t is thus an approximation of x of t. The difference between them is called a quantization error or quantization noise. So for example, so x of t is the input signal and xq of t is the quantized signal. The xq of t minus x of t is the quantization error or quantization noise. The difference between quantizer output minus quantizer input we called as a quantization noise or quantization error. This error should be as small as possible. To minimize the quantization error, step size S or D should be as small as possible. So this is the step size as small as possible, which is done by increasing the number of quantization level. So for example, in this particular example, quantization level is 8. So if you increase the quantization level 8 to 16, the error will be reduced. The quantization is classified into mid-thread quantization and mid-range quantization. In mid-rise type of quantization, let's consider output voltage level. This is the output voltage level and this is the input voltage level. So in mid-rise type of quantization, this is the rising edge. Rising edge is lies between the origin of the input and voltage levels. So this is the origin and this is the midpoint of the rising edge. The midpoint of the rising edge is lies between the origin. This type of quantization process is called as a mid-rise type of quantization. In mid-thread, so this is the threading, the origin is lies in the middle of the thread. So this is the origin and this is the thread and this is the middle point and this is the voltage level and this is the input level. So threading is lies between the origin. This type of quantization we called as a mid-thread quantization. Now we will look into quantization noise. The use of the quantization introduced an error is defined as the difference between the input signal M and output signal V. This error is called as a quantization error or quantization noise. So let's consider input wave and this is the input wave. One is the input wave and two is the quantized output. So our main here we have to find out the quantization noise. So quantization noise it's equal to output signal minus input signal, or so this is the input signal and this is the quantized output. So this is the error. The error, this is the error, it's equal to quantized output minus input wave. For simplicity, let the quantization input m be a sample value of a zero mean random variable m. The quantizer g of dot maps the input random variable m of the continuous amplitude into a discrete random variable. Let quantization error be denoted by a random variable q of a sampled value small letter q. We may write the q is equal to m minus v, or it's equal to q, it's equal to m minus v. With the input m having a zero mean and the quantizer assumed to be a symmetric, it follows that the quantizer output V and therefore the quantization error Q will also have a zero mean. The error, it's equal to quantization error denoted as Q, whether it's a small letter q or big letter q, it's equal to m minus V. So m is the output and V is the input. In order to find the output signal to noise ratio, we need to find the mean square value of the quantization error. Let consider an input m of the continuous amplitude in the range minus m maximum to m maximum. So minus m maximum is the lower voltage level and m maximum is the highest voltage level. Assuming a uniform quantizer of the mid-rise type, we find the step size of the quantizer. The quantizer is given by delta is equal to 2 m maximum divided by L. So we know that delta is the step size. It's equal to highest voltage level VH minus lowest voltage level divided by L. So in this particular case, the highest voltage level VH it's equal to M maximum and lowest voltage level VL it's equal to minus M maximum. So VH minus VL it's equal to 2 into M maximum divided by L, where L is the total number of representation level. For the uniform quantizer, the quantization error Q will have its a sample value bounded by minus delta by 2 less than or equal to Q or less than or equal to delta by 2. So here quantization error is less than or equal to 50%. So for example 1.68 its round of value it's equal to 2 and 1.3 it's equal to 1. The approximation is less than zero point 0.5. The bounded value in between minus delta by 2 or less than or equal to q or less than or equal to delta by 2. If delta is sufficient small or L is sufficiently large, it is reasonable to assume that the quantization error Q is a uniform distributed random variable. The probability density function of the quantization error is Q. Now, the probability density function of the quantizer error Q as follows. The quantization error, the probability density function Fq of Q is equal to 1 by delta when Q is greater than minus delta by 2 or less than or equal to delta by 2. Otherwise, probability density function it's equal to 0. So we know that the range it varies from minus delta by 2 to delta by 2. So this is the value of the Q. We have to find out the probability density function. So let's consider on spectrum, this is A and this is B. Area of the spectrum, it's equal to 1 divided by B minus A. Here in this particular example, so it varies from, the range varies from minus delta divided by 2 to delta by 2. So in case of probability density function, we have to find out the total area. So we know that, so B is equal to delta by 2 and A is equal to minus delta by 2. Now just you replace B is equal to delta by 2 and A is equal to minus delta by 2. So here 1 divided by B minus A, it's equal to 1 divided by delta, when Q varies from minus delta by 2 to delta by 2. So probability density function, it's equal to 1 divided by delta. Now the variation of the quantization error sigma q square is equal to minus delta by 2 to delta by 2 q square into fq of q dq. So this is the variation of the quantization error. In general, the variation, the mean variation, it's equal to x square ex square, it's equal to integration minus infinity to infinity x square f of x into dx. So this is the general equations for variation of function. So here x is equal to q, x is equal to q, and this is a probability density function, it's equal to fq of q. So this is the mean variation, and here in general case the limit varies from minus infinity to infinity. In this particular case, the variation or range varies from minus delta by 2 to delta by 2. So in generalized equation, E is equal to x square, it's equal to minus infinity to infinity x square into f of x into dx. So here x is equal to q, x is equal to q, and infinity is equal to delta by 2. Just to modify this equation, the mean variation is equal to sigma q square is equal to integration minus delta by 2 to delta by 2 q square fq of q into dq. Now you substitute fq of q values. So we know that fq of q is equal to 1 by delta when q is greater than minus delta by 2 and less than delta by 2. So limit varies from minus delta by 2 to delta by 2, and q value is equal to 1 by delta. So after substituting, we get mean variations sigma q square is equal to 1 divided by delta integration minus delta by 2 to delta by 2 q square. So fq of q is equal to 1 by delta. So 1 by delta is a constant factor, you take it outside. So dq. Now you integrate this. So integration of minus delta by 2 to delta by 2 q square. This is the finite limit. So q square is equal to q cube divided by 3, and limits varies from minus delta by 2 to delta by 2. So it's equal to upper limit minus lower limit. Just you replace q is equal to delta by 2, you find out the value. So after integrating, so we get sigma q square is equal to delta square divided by 12. So delta square by 12 is the quantization noise. Typically, L is array number, K is denoted the kth representation level of the quantizer that transmitted to a receiver in binary form. Let R is denoted the number of bits per sample used in the construction of binary code. So here L is equal to 2 to the power R and R is equal to log base 2 of L value. Now you substitute into equation. So delta is equal to 2 maximum divided by L. It's equal to 2 maximum divided by L is equal to 2 to the power R. So this is the step size. The step size is equal to 2 maximum divided by 2 to the power R when range varies from minus M maximum to plus M maximum. Our main intention is to find out the signal to noise ratio of the uniform quantizer. The uniform quantizer, the signal to noise ratio is equal to P divided by sigma q square. Let the where P is denoted the any power of the message signal m of t. We may express the output signal to noise ratio is equal to P divided by sigma q square. So SNR output it's equal to P, this is the power, divided by sigma q square. So we have to find out the sigma q square value. So we know that sigma q square it's equal to delta divided by 12. So we know that delta it's equal to 2 into m maximum divided by L, it's equal to 2 m maximum divided by 2 to the power R. So now you replace delta into equivalent value. It's equal to, so delta is equal to 2 m maximum divided by 2 to the power R whole divided by 12 whole divided by 12. Just you simplify this equation. So after simplification we get 1 by 3 m maximum into 2 to the power minus 2r. So this is the equivalent value for sigma q square. So our intention is to find out the SNR output. So SNR output is equal to P divided by sigma q square. Now you replace sigma q square into 1 by 3 m maximum 2 to the power minus 2r. So after simplification, so we get SNR output is equal to 3 into P divided by m square m maximum square into 2 to the power 2r. The SNR output of the quantization noise is equal to 3 into P divided by m maximum square into 2 to the power 2r. This above equation shows that the output SNR of the quantizer is increases exponentially with increasing of a bit per samples. So number of bit is R. These are some references. Thank you.